Okay, last class we ended with a couple of different, we ended with reactions of Grignard reagents with some different carbonyl compounds, remembering that one was the reaction with CO2, and CO2 has that electrophilic carbon as well. The only difference between this and a reaction with a normal carbonyl group is that we end up with a carboxylic acid. If we react with an aldehyde, we get a primary alcohol. Here's just a couple of examples. If we react with an aldehyde other than formaldehyde, we get a secondary alcohol. Again, notice in these slides that one of the nice things is they have different colors for the starting materials, and you can kind of see on the framework which starting material those came from. So that's our secondary alcohol. If we add a Grignard to a ketone, we get a tertiary alcohol. And if we add a Grignard to an ester, we need two equivalents of Grignard, and we get, let's just remind you why. We have our ester. I'm going to use this ester. So we get our attack at the carbonyl compound. We form what we have been calling our tetrahedral intermediate. And we don't want to forget that the magnesium is still around there, but we have a tendency, that's not the part we want, and we have a tendency to just let it drop by. The other thing too is that in solution the magnesium is going to end up coordinating that oxygen. And we're typically in organic solvents, so we have a messy, it looks like a messy reaction. Everything is working, but it looks messy. And we have our magnesium salt, but this can just kick off the alkoxide. And so long as we have two equivalents of Grignard reagent, we're going to keep going because our product, our initial product, is just a ketone. So we get addition to that with our second equivalent. So I'm just going to put 1, 2, and we get and then this will just sit around until we do our workup. And when we finally do our workup, we get a tertiary alcohol. So we now have enough, you guys are building up an arsenal of reactions that you're learning, and you're getting to the point where you can start thinking about synthesizing bigger molecules from smaller molecules, particularly now that you're learning about how to form some carbon-carbon bonds. So when we can build carbon-carbon bonds, we can build bigger molecules. And for organic molecules, we need to be able to form carbon-carbon bonds to build bigger molecules. And then there's other things we put on the organic molecules, the stuff that makes them important for whatever their function may be it a biological function, a medicinal function, maybe a materials function. And a lot of times that requires atoms other than carbon. So here's a molecule we may want. How do we plan a synthesis? We know what molecule we want. We just kind of work backwards. And so we take a look at this and we say, well, there's a tertiary alcohol. I could make that from Grignard reactions. So then we just have to start thinking kind of backwards and this is what we call retrosynthetic analysis. We work backwards. So we can disconnect here, and if we disconnect there, we have this portion of a molecule which we can bring from a ketone, and this portion of a molecule which can come from our Grignard. So we just work backwards, and then the synthetic part is going forward. The synthesis is just to take our compounds, add the reagents that we need. This is actually a solvent, and then we work it up with acid. So we think retrosynthetically. Now these are simple retrosynthetic analysis because they only involve 1 or 2 steps. You can imagine that as we build bigger and bigger molecules, we may start at a molecule and go backwards and backwards and backwards until we reach small molecules that we have in our lab or that we can buy relatively cheaply. Now, for this particular molecule, we could have done a different disconnect. We could have done this disconnection, and then we have the methyl group and the phenyl group and the oxygen. That can come from this ketone and this Grignard reagent. So not only that, so then we can just work forward. But from a retrosynthetic analysis standpoint, what if we didn't have any of this ketone in our lab? We didn't have any of the precursor from the last reaction. Well, maybe we can go even further, and because we've already seen that we can make that ketone in situ by reacting with an ester, so our retrosynthetic analysis, we could have also disconnected both of these. We get this portion, and from that we will add 1 methyl magnesium bromide to get the ketone and then the additional one. So be aware that when you're planning a synthesis, two people may come up with different syntheses for the same molecule. Both will be valid, potentially, 2 or more. So there's lots of ways to make compounds, especially as it gets more and more complicated. As we add more and more steps, some of us may come up with different synthetic procedures than others, and both being equally valid. And what would drive which one we choose? How easy they're to do in the lab, how expensive our materials are. As well as now, what's really be taken into account, we talk about green chemistry, and that is maybe we have a slightly more expensive pathway, but it's very environmentally friendly. We're probably going to choose that. So a lot of analysis goes into the synthesis of larger molecules. We do have to be aware of the restrictions that we have with Grignard reagents, okay? So they're not only good nucleophiles, they're strong bases. So the fact that they're strong bases means that we don't want anything that's slightly acidic. Because they're very strong bases, they will pull off even only moderately acidic hydrogens. And we've seen that at that one example where we reacted a Grignard with a terminal alkyne to pull off that hydrogen from the terminal portion of the alkyne. Remember what that we said. This is slightly acidic, and as it turns out, a Grignard is a strong enough base to pull that off. So we cannot use that functionality if we want to use our Grignard for another portion of the molecule. So they're useful nucleophiles, but they're also strong bases. So we can't prepare a Grignard from a compound that contains a hydrogen more acidic than hydrogen atoms of an alkane or alkene, because that's where our Grignards come from. We can't prepare it with any of these. These are all activated hydrogens these are quite acidic. This much less so, but still compared to a hydrocarbon, it's very acidic, and a Grignard reagent will pull that hydrogen off. We also can't prepare a Grignard reagent from any compound that has the functionality that we wish to react it with. So in other words, Grignards react with these. We've seen that. We've been looking at those reactions. So if we had some molecule, for instance, this molecule, if we tried to make a Grignard from this molecule, it's just going to react with itself because it has a place over here it can react with, and you'll end up with this intramolecular reaction rather than being able to use this to attach it to other molecules. So all of these functional groups are incompatible with making a Grignard reagent at another portion in the molecule. So we are talking about multifunctional molecules, molecules with multifunctional groups. So we have that alkyl bromide somewhere. We can't have any of these functionalities elsewhere in the molecule and make a Grignard reagent. Lithium reagents react exactly like Grignard reagents. It's all the same. We have a nucleophilic source of carbon. These things are also strong bases. They're even stronger bases than Grignard reagents. These are more reactive than Grignard reagents, so sometimes we need that extra punch. They react the same. In terms of carbonyl compounds, they'll seek out the electrophilic carbonyl carbon, and we get our tetrahedral intermediate, and then we usually end up working it up with slightly acidic conditions. One of the reasons we don't use them, they're a little bit more difficult to prepare, they're a little bit more dangerous, but you know, they're not something that you necessarily need to avoid if you're an organic chemist. You just have to be aware and be safe. Sometimes we've talked about this being slightly acidic. Here's another base that can pull off that hydrogen, sodium amide. NH2 minus is the base here. And that's a strong base. Relatively strong base. And when I say a strong base, we actually wouldn't be able to dissolve this in water. Why would we not be able to dissolve it in water, might anybody think? What would happen if we tried to dissolve that in water? Is water an acid? How many people think water is an acid? I should see everybody's hands up, right? Water is an acid. You could pull a proton off water. If you pull a proton off water, what do you get? What's left over? You guys are very quiet this morning. Okay. If we pull a proton off of water, let's pull this proton off. Let's do it with NH2 minus, okay? We end up with a hydroxide ion, right? Okay, so water is an acid because it has a proton that can be removed by a base. However, we can use sodium amide in nice non-protic solvents. It is a strong base. It's strong enough to pull the proton off a terminal alkyne, and then we get another source of nucleophilic carbon. We get this sodium alkanide. And they're strong bases, yes, because it's the conjugate base of this reaction. This is just an acid-base reaction, like any acid-base reaction. This is our base, this is our acid, this is our conjugate base. What's our conjugate acid? Well, it's ammonia, NH3. It's not shown here. But this thing is also nucleophilic. We have negatively charged carbon, and it can react with electrophiles such as carbonyl groups in the same manner as the rest of them have done, where we get formation of a carbon-carbon bond here. We get this tetrahedral intermediate that we can work up, and we end up getting this, in this case, a tertiary alcohol. So that looks a lot like a Grignard reaction as well. One of the things we have to start thinking about is, you know what, maybe we want to make some compounds that have some functional groups that are getting in our way. We can protect them. We can add protecting groups. So how would we make this? We can't use a Grignard reagent. We can't make a Grignard reagent out of this because when we try to make our Grignard reagent, we're just going to end up, that's going to get in the way. So how might we do it? We protect that reactive functional group. So we're going to talk about protecting alcohols here, but we do our retrosynthetic analysis. This is the problem. We cannot make this compound, okay? We try to make this compound, and this is going to react with that, we're just going to get a mess. So we need to protect it. So this is what we're talking about. As soon as we make that Grignard reagent, it's going to react with that acidic proton, and we're going to end up with just an alkoxide salt, nowhere near what we were trying to do. So we need to protect that first OH group. We just add something to it. We remove the proton and we add something else. Then we go ahead and make our Grignard reagent. We add that to whatever our substrate is. In this case, we wanted to add it to acetone to make a tertiary alcohol. And then at the end, we remove our protecting group, and we have in effect, made a Grignard reagent out of this. But we had to protect that functionality. Okay? So we're getting to the point now where we can build up larger molecules. Quite often we're going to have multiple functional groups on there, and we have to start assessing, is that functional group going to get in the way of my reaction? If it is, can I protect it? Alcohols, turns out there's a lot of protecting groups for alcohols. Here's a very common one, T-butyl dimethylsilyl chloride. We used to have a professor here, he's now at St. Mary's, but he used to talk about why this reaction goes. Well, silicon likes oxygen, like ketchup likes potatoes. So that's not mine, that's Clyburn's. But anyway, this reacts with an alcohol to form this protected alcohol. It's quite unreactive, but also easily removed. We can then go ahead and do a bunch of chemistry on our compound, and at the end, this particular group we can remove. We just have to use this reagent, and it removes the protecting group. The fluoride grabs hold of the TBS group and pulls it off, and we end up with an alcohol. In this case, a diol. So that's the end of chapter 12. Any questions about the chapter? I wanted to talk a little bit about the quizzes. I hope to have those most of the time. I will return them on Monday mornings. I will release a sapling assignment tonight. There are a few multi-step syntheses on the end that are a little hairy. Don't worry too much about them. I may remove them. I'll take a look at them again. I may remove some of those. So that'll be released tonight. And I will post chapter 12 now that we've completed. I will post it on the website, Acorn. The next chapter we're going to do with right away is chapter 16. And chapter 16 is aldehydes and ketones, nucleophilic addition to the carbonyl group. So, interestingly enough, yes, it'll be due Thursday at 11:30 p.m. Okay, next Thursday. That'll be the due date all the time. Interestingly enough, the textbook we have been using for a number of years introduces that chapter 12, which is a lot of carbonyl chemistry. Then it does a bunch of stuff, and then it reintroduces carbonyl chemistry. And I decided it's much more useful for you folks, especially anybody that's taken biochemistry, to get into more carbonyl chemistry now, because you'll be using a lot of it in biochemistry. So we're skipping right to chapter 16, which is aldehydes and ketones. This whole chapter is about nucleophilic addition to the carbonyl group for the most part. We're already familiar with the carbonyl functionality, especially in terms of aldehydes and ketones. An aldehyde is a carbonyl group that has at least one hydrogen on it. If it has two hydrogens on it, it's a special kind of aldehyde. It's formaldehyde. Ketone has the carbonyl group bonded to two other carbons. Okay? And we have talked about esters as well, and we're going to start talking about other things like acid chlorides and anhydrides. So we're going to get into that in the next couple of chapters. Nomenclature, there's on Acorn, if you go into that book, the next second chapter of the book, that the Acorn book, has some links to some nomenclature. I expect you to know how to name these things. I don't get really excited about asking a lot of nomenclature questions, but there'll be a few simple ones. So for aldehydes, IUPAC, aldehydes have the ending AL. Ketones have the ending ONE. We always number the longest carbon chain containing the carbonyl carbon. We don't necessarily start at the carbonyl carbon, but we always make sure that the carbonyl carbon has the lowest number it can. For instance, in this particular compound, which is a ketone, we start 1, 2, 3, 4, 5, 6, 7. This is 6 bromo, 4 ethyl, 3 heptanone. We could have started numbering from here, but then as naming it from a ketone, we always try and get the number as small as possible. That's why this is not carbon number 1 if we name it as a ketone. And it's a heptanone because there's 7 carbons. We could also call this thing an ethyl 1, 2, 3, 4 butyl ketone. That's another way of naming them. So there's lots of different ways of naming them that you'll have to get used to. For aldehydes, obviously the aldehydic group starts at carbon number 1. Because aldehydes are different, they can be terminal groups, so it will always be number 1. And that's all I'm going to do about naming. Take a look at those naming sections. Properties of our aldehydes and ketones. So here we're just talking about boiling point. We see butane. Butane is a gas at room temperature. And as soon as we start adding functionality, propanal, if we had butanal, it would be even higher boiling, but propanal boils at 97. Why does this have such a high boiling point? You guys have talked about this in first year chemistry. What does this give us opportunity in terms of intermolecular reactions when you have an OH group? What's hydrogen bonding, right? So that's the strongest intermolecular force. It's a polar compound, and it also has activated hydrogens that can take part in hydrogen bonds, so alcohols tend to be quite high boiling. Ketones and aldehydes are higher boiling than their counterpart alkanes, but not as high boiling points as their alcohol counterparts. So all of these things have fairly similar molecular weights, and we see that the ketones are somewhere in between a pure alkane and something with an OH group. So we have a polar group, and intermolecularly we can get polar-polar interactions that cause that boiling point temperature to go up a little bit, because there is that dipolar intermolecular attraction. We've already talked about some of the ways we can make them. We can oxidize alcohols to get aldehydes and ketones. We already know that although we can oxidize a primary alcohol to get an aldehyde, we have to use special reagents, so we avoid going too far to the carboxylic acid. A lot of this is review. This is a review from a reaction from last semester. So I always get some emails about what do I need to know from last semester. Well, you need to be comfortable with last semester's material. We'll remind you of some stuff, but there's a reason why you have to take Organic 1 before you take Organic 2, and that's because we expect you to be comfortable with the material from Organic 1. Here we react ozone with an alkene, and if we think about this, we can remember all we really do is we're kind of splitting this bond and adding an oxygen to each side of it. That's what happens when we do the ozonolysis of an alkene. So we get, in this case, these two aldehydes. And synthetically, that's pretty useful. Now, here's a couple of reactions, a couple of examples. So if we were to take this alkene and react it with ozone, work it up in dimethyl sulfide, we'd end up with this ketone and this aldehyde. If we were to take this alkene, do the same reaction, we end up with this aldehyde and this formaldehyde. Now, I just want you to think for a minute, taking a look at these two reactions, thinking from a synthetic chemist standpoint, right? We want to make a particular molecule. We think of a reaction to make it. In the lab, we have to work it up, and purify our compound. So why might this reaction be synthetically useful? This one's not particularly synthetically useful. Why might this not be synthetically useful? Okay, we could make it. Do you think that's going to be an easy purification step? We have two different compounds, neither of which are, this one might be water soluble. It is slightly water soluble. This is really water soluble. This is not, okay? So for this particular reaction in the bottom, we've made our organic compound. We have an easy way of cleaning it up. We can get all the crap out by washing. We use an organic solvent that's not miscible with water, and we wash it up. And this part of the, this side product, we can easily get out. And in this one, it would be more work to separate these two compounds. Let's say we wanted this one. We'd have to figure out how to get this out. We could. It would be a pain. This would not be much of a pain. Now, what would be another nice synthetically useful step if we wanted to make one of these compounds? Another way might be to start off with a symmetrical alkene so that the two reagents are the same, or the two products are the same. So if we had for instance, there's an example of a fairly useful reaction because we're just splitting this up and the two ketones that we get are the same ketone. We only get one ketone, but we get two equivalents of it. So those are things you need to think about in terms of synthesis. Is not only can I make what I want to make, is it going to be easy to clean it up? Aldehydes can be made by reducing. We've already seen that we can get aldehydes by reduction of these compounds, but typically they don't stop there. So we can make aldehydes by using a reducing agent. Lithium aluminum hydride's an animal, okay? It's just very reactive. It reduces everything in sight. So as soon as we make that, aldehyde is going to get further reduced to the alcohol. So we need to come up with ways of doing the reduction and stopping at the aldehyde. I want to, no, not here, okay. So there are reagents that we can use. Two aluminum hydride derivatives, they're less reactive than lithium aluminum hydride, and they're less reactive because we've bulked them up, and notice now we only have one hydrogen bonded to that aluminum. So each reagent can only do each molecule of reagent can only reduce one carbonyl group. Lithium aluminum hydride has 4 hydrides to it, and every one of them ends up getting transferred to something and reducing it. This one, it only has 1. It also has some added benefit. We've bulked it up, so it's not nearly as reactive as ALH4. This is much less reactive. It's still reactive. It still likes to deliver that hydrogen as an H-. Same with this compound. This is a neutral diisobutyl aluminum hydride. We call it dibol. It also, where our R is an H group, and it can deliver a hydride. One of the things I want to, so we can do these reactions. We do them at low temperatures. The reason we do them at low temperatures is that these things are still reactive. They can be reduced. If we did it at higher temperatures, this reaction becomes very fast. These can still be reduced by these same reagents, but if we do them at low temperatures, that reaction is slow enough that we can complete the first reaction before the second reaction kind of goes to any degree. So we do them at low temperatures. Here's 3 examples of things we can use to make aldehydes using these special reagents. One of the things I also wanted to show you, okay, so number 1, why this works, but also when you get the notes afterwards when I post them, what you will find is sometimes I put a lot of information down here with links to websites as well. So particularly if I steal something from the internet, I have to source it. I have to tell you where I got it from. This particular diagram I got from this website, and if you go there, it talks a little bit more about this reagent. So this reagent Dibal works very well. Oops. And it's discussed in the notes why it works very well. But one of the reasons it works very well is this actually works a little bit differently. Lithium aluminum hydride is a source of hydride that is nucleophilic. But in fact, the first thing that happens is this reagent acts as an electrophile. That's the first thing that happens. It actually does coordinate to the oxygen to form this kind of complex in solution before the hydride gets delivered. Then the hydride gets delivered to the carbonyl carbon, and we end up with this thing. This thing, as it turns out, is actually quite stable and will just stick around. Okay? So that's what's nice about this reaction, is this just sticks around, and then we have to work it up to get our final product. So this isn't even available to be reduced in this particular reaction step. And that's why we can use Dibal to reduce an ester to this compound. Then during the workup is when we get our aldehyde, and our aldehyde is not around to get further reduced to an alcohol. This is just the same thing. This was the notes from your textbook, and I just left it there. We can also get aldehydes from these things which we call acyl chlorides. We can make those using this thing called thionyl chloride, and we're going to talk more about this particular reaction in the next chapter when we talk about carboxylic acid derivatives more fully. But we can, from a carboxylic acid, we can easily make this acyl chloride, and then we use this lithium triterbutoxy aluminum hydride. We've just bulked up the aluminum hydride, we've made it less reactive, and we do the reaction at minus 78, and we again end up stopping at the aldehyde. This is just another example. We usually do these things in ether, and can anybody, we want to go to quite cold temperatures. We use minus 78 a lot. You guys probably don't know why we use minus 78. Why don't we use minus 75 or minus 81? Okay, this is, I don't expect you to know this, but as it turns out, you can make a carbon dioxide acetone bath that ends up being at minus 78. That's why you see a lot of reactions done at minus 78. Just happens to be a temperature that's easy to get to in the lab using a little bit of trickery. Okay? So that's why we use that temperature a lot. No other reason. So don't think that if you did this at minus 72, it's going to be a big mistake and you're going to end up with a horrible yield. In fact, a lot of times now we use mechanical things to lower our temperature rather than dry ice and different solvents to make cold temperature baths. So we can make aldehydes from acid chlorides. Here we see the reaction and the mechanism. So what's happening? Kind of the same thing. The first thing that happens, and the reason this reaction works well, is this is a salt, okay? This part is the negative. The aluminum hydride with the 3 T-butoxy groups is negative. The lithium is positive, and the lithium kind of coordinates our oxygen, activates it. The reaction goes quite readily. Then we get our hydride transfer to make this compound, and what ends up happening is that all of this happens very close together, and you end up, the lithium ends up coming off because the aluminum is now neutral. It's quite electrophilic, and it wants to just form this complex. this complex is more stable than this complex, so you get this rearrangement. And the nice thing is that we now kick off our chloride, and we end up with this thing, and we finally work it up. So what ends up happening is our aluminum ties up our products, and all of this happens fairly fast to here. This thing could be reduced, but it's all tied up, and another lithium is not going to come in and tear this apart and allow another reagent to come in and cause this reduction of this aldehyde to happen. That's why it works. We end up getting this complex, and we have these big bulky groups. This would be reactive, but we have a lot of bulk around there, and so another reagent with a hydride, another one of these things, just can't access this for the reaction to occur. We bulk it up, and then we just, at the end, we react this with a little bit of acidic acid and water and free up our aldehyde and do the workup. So we do a little bit of trickery. We have a nice reducing agent, and in fact, if we start with an aldehyde, we can use these reagents to reduce aldehydes, but we don't need these. These reagents are a little bit more expensive, they're not that hard to work with, actually. They're easier to work with than lithium aluminum hydride, but if we're just reducing an aldehyde, we would just use lithium aluminum hydride or sodium borohydride. We don't need these expensive reagents. We use these when we want to stop at the aldehyde. We can also make aldehydes from esters and nitriles, and I'm just going to show you these reactions. We're not going to get into them too much just yet. I want you to be aware that they can happen, and they look a little bit different because here we have a nitrile. Nitriles are nucleophilic because they have this lone pair of electrons in the nitrogen, and that ties up with our aluminum to form this thing. The mechanism is the same. This is dibol. Dibol then delivers the hydride to this carbon, which has become electrophilic. This is very much like a ketone, except that instead of a carbon-oxygen double bond, we have a carbon-nitrogen double bond. Once we coordinate it, we could draw a resonance structure which puts that positive charge on the carbon, so that's a very electrophilic center. We deliver our hydride to this thing, and we end up with this. When we react this with water, the nitrogen ends up getting replaced by an oxygen, and we'll talk about how that occurs next class, because I don't really want to get into it just yet. But that's another way of making aldehydes. So here's some examples. Now this is an interesting example. I want you to take a look at this as well. Take a look at this. How many people are in biochemistry now? Have you started carbohydrate chemistry? Okay, you haven't. This looks a lot like a sugar, okay? Sugars can be these cyclic compounds, and we end up with an OH group and an aldehyde group. Although we can make this coming from there, we have to be very careful because this thing can go back to there quite easily. We get a reaction of our hydroxy group can attack that carbonyl, and it's a little bit different. We get a hemiacetal. Sorry, it doesn't go back to that. It goes to a hemiacetal. But this thing is very much like a sugar. Again, we can just reduce, in this case, a nitrile, in that case, an ester, using these special reagents to stop at the aldehydes. Ketones, we've already seen that we can make aldehydes by doing the reaction with ozone, and we did an example where we made a ketone with the ozone. That's a fairly common way to make ketones as well. And again, these are just examples. Don't forget that whenever we do this, we just have to think about cutting this bond and adding oxygen to both sides. And that's what we get here, is this dicarbonyl compound. Same thing here. We'll split that there. We'll get acetone and this aldehyde. This is a reaction we're going to examine in great detail in a few weeks. We react an acid chloride with an aromatic benzene. We can have substituted benzenes. And what ends up happening is we substitute one of these hydrogens, gets replaced by this acyl group. This is called electrophilic aromatic substitution. And we have a whole chapter talking about this particular reaction. So be aware now that we can use it to make ketones, and we'll talk about it in detail later. We've already examined this reaction where we can oxidize a secondary alcohol to the ketone using Jones reagent or chromic acid or pyridinium chlorochromate. We can also make ketones from nitriles, and this is very similar to that last reaction in that we end up taking this thing, reacting it with water and acid to make the ketone. So we'll talk about it in a little more detail in the next class. And I think I'm gonna stop there, because the next thing I do want you to think about this retrosynthetic analysis. It's in your notes. So suggest a synthesis of this compound from these two things. And you've got to think backwards, because one of the things you'll notice is that we have to add some carbons here. Okay, because we have 1, 2, 3, 4, 5 carbons, but our 1, 2, 3, 4. So we have to add another carbon somehow.